hours. It took a minute to firm that up, but you will see they are Monday, Wednesday. Friday's kind of, I don't know if I'm keeping that one, but Monday, Wednesday, 11 till noon. It's more like 11:15 to 12:15 because I know some of you have 10:10. I think some of you have 10:10. And historically, students have had class from 10:10 to 11, maybe a calculus, and you have to walk over. So I don't want to start at 11. I want to make sure you have the benefit of having the 15 minutes to get to me, and we go the full hour starting at 11:15. The benefit of me. That sounded great. And the other two are on Zoom because I have a couple of graduate students. It's a little bit easier, I think, for them to do it that way. So we'll go from there. So last time, quick review, we discussed vector analysis. I'm recording and I am live. Can everybody see my screen? I'll take that as a yes, unless I hear differently. After a few, really not very long at, I got chat again. Yes. So after about, I don't know, 15 minutes of vector analysis, vector algebra, scalar product, cross product, which I think most of you, all of you, frankly, will remember from PHY 2048. We went to the first non-trivial operator we encounter in this class, and that is the del, nabla, whatever you want to call it, operator. I have stuff in the way. I can't even see my own thing. And we'll move this over here. And we talked about its definition as grad is I hat partial partial x, j hat partial partial y, k hat partial partial z. That is an operator waiting to do something. And what it is waiting to do, you know, Stephen, I forgot to tell you of all people that I don't have a vehicle today. I'm sorry, I apologize.
Oh, it's all good. I
I
actually
can't hear you.
couldn't make it. I
I'll
couldn't
say
make it
that,
to the.
you were probably there anyway, so I apologize. I told all the students knew but you. So I'll make sure I put you on a master list somewhere. So Nabla F or whatever you want to call it. I call it grad in this class is something that transforms a scalar function into a vector function. We cheat you, by the way. I'm going to just put this in your head now. It will mean nothing to you unless you continue in this for quite some time. What grad is actually not a vector. What we have in physics cheated you out of is the magnificent structure of vectors in one forms. A dot B is an artifact of the fact that we're in three dimensions and define that nice and pretty. But really, what this should be is a contravariant vector and a covariant vector in the general form, or a one form and a vector. That's how you actually make cross dot products and scalars out of things. Okay. And I said that the vector that results from taking the gradient of f is defined as something that is normal to the, not defined, it comes out to be normal to the surface defined by f of x, y of z is equal to a constant. And I gave you the example of a sphere. If it's less than one, you have a solid ball. If it's with an open boundary, if it's equal to one, you've constrained the points x, y, and z to lie on the surface of a sphere. So we started an in-class example. We also had an ellipse over here. So I said, look, let's look at this and let's calculate the vector that comes from grad of s of x and y, which is right below it. I'll do it here. So I'll call this v. And if I do that operation, I get I hat 2x plus j hat 2y. And I will remind you that a partial only hits the variable upon which it is operating. So we have v of x of y now. Write this a little bit different. 2x I hat plus 2y j hat. So now let's construct our table. I'm only doing 3 points, but I'm going to draw in several more. So let's do it. When x is equal to 0 and y is equal to 1, this is 2j hat. 2j hat, here's x is equal to 0, y is equal to 0, right here, that dark dot. X is equal to 0, y is equal to 1 is right here. And that points upward in this direction. So far, so good. Let's look at 1, 0. 1, 0 will be this point, and that will be 2 I hat. and that points this way. And then minus 1 over root 2, and then 1 over root 2 will be here on the circle. Notice that when I square those two, I get 1 half plus 1 half is 1. So I am on the surface. Surface in this case being the surface of a two-dimensional disk. So if I do that, I will get minus, put that in here, I'll get square root of 2 I hat plus, put 1 over the square root of 2 here, I get square root of 2 j hat. That is an equal amount of I hat and j hat in magnitude. Watch me for a second. This goes this way. This goes this way. That doesn't really help anything. The x hat component is negative, and it has 1.414 whatever. So this way, and then 1.414 up. So at that point, I come here and an equal amount up, and I point here. Notice in each case, the magnitude of the vector is 2. You can normalize later if you want. It doesn't take long to figure out if I put in 1 minus 1, I'll come down here. If I put 1 over root 2, 1 over root 2, I'll put here, and so on. And now what I've seen, and I'm not drawing all of them obviously, because there's an infinite number, it would take a minute, is I have constructed a field of vectors normal everywhere to the surface described by x squared plus y squared is equal to 1, namely a circle. If this is a sphere, what you're going to get is something that looks like a hedgehog. I don't know if that's what just maybe a pincushion, whatever. But what you'll have is vectors pointing everywhere out. Think of the surface of a sphere and putting in needles everywhere normal to the surface. So if I was on the surface right now, I could take my hand or go on the floor. I'd put this down. I'd put this down. Now, the fact that it's not normalized is not that important. You will sometimes normalize it, sometimes you won't. You don't care. In fact, later on, we'll find out when we take the gradient of the potential to give us the electric field, we don't normalize anything. That's the definition of it. But if you want a normal vector field, you can sit here and normalize everything. So I told you once you've seen the example, I would revisit why it's normal. And I'll show you this is a quick derivation. So I'm going to use S this time. Here's S of X, Y, Z. I'm going to use F. Here's F of X, Y. This S was just for that specific circle. Is equal to a constant. If I take the differential, so everywhere on here, that has the same value. Here's a value, 1.7093. So everywhere on this surface, that's 1.7093, no matter where I go. Doesn't matter. So if I ask how much it's changing on that surface, df, that is going to be the differential of a constant, and we know the differential of a constant is 0. If I ask what df is, df, as we saw earlier, is equal to d back here. Let's go back and look. I don't know, I wrote it down. Yeah, right here. So df is equal to, for any function, in fact, I'm going to review that because I don't know who knows what in this class. So the differential of any function is dx, the total derivative, if you will, of any function. And we're going to exploit this idea very often. So let me remind you the total differential, this d operator, you can also think of that as dx partial x plus and so on. If you look at this, this is actually the same as dr dot grad f, because this is dx. So I'm being very explicit here. That is the total differential of a function. And I'm not going to be writing those out. These two are the same thing. I hat dot I hat is 1, j hat dot j hat is 1, k hat dot k hat is 1. All the cross terms are 0. Well, I'm going to tell you that this is the product of two vectors, which is the magnitude of dr, magnitude of f, grad f, times the angle between them, cosine theta. And I have just told you that if you are on a surface define that f of x by f of x, y, z is equal to a constant. No matter how you travel around over here, take a walk, look, look. Think of it as temperature if you want. It's 20 degrees here, Celsius, 20 degrees here. You walk all over. No matter which way you go, no matter what little step you take, and the little step you take is dr on that surface. If you take that step, you get 0, which I've just said is dr grad f cosine theta. If you dot two vectors together, the only way you can get a 0 if both of them are non-zero is for what? For them to be perpendicular. In other words, I have to have cosine theta kill everything here, or cosine theta then is equal to 0, which means theta is pi over 2, or 90 degrees. So that's why everywhere on a surface of constant value, real quick, you have to be a little careful about that dr. That dr really it's a technical point, but that dr, if you want to stay in the surface, you got to, no matter what you do, if you're in the surface, the dr should stay on the surface. But this is a nice general argument to show you the point that that cosine theta has to kill off the vector product and you're good to go. Okay, so that is our first vector operation. And what I would like to tell you is you should remember this. Yields produces normal. This is the takeaway point. I'm going to give you those 4x6 cards. Everywhere constant, everywhere normal to a constant surface. I just keep using, I'm using S in another class because it's entropy. And that is a rectangle worthy statement. It's a rectangle worthy statement because, as you may or may not remember from general physics, it depends. I don't know who did it or who did not. I have to not do it because of time considerations to get anything done. But the electric field is the gradient of the potential up to a minus sign. Okay, good. So that is our first vector operation. I applaud you. You got this far in the class. The second vector operation is now where it's kind of now where you go to yourself, man, I did not sign up for this. You did. Yes, you did. You did sign up for it. So don't panic. All right, let's look. The next operation is the divergence that is simple to write down, much more complicated to interpret. I get a stronger V. And writing this out explicitly, I won't write all three components every single time. And I'll take a little bit of an abbreviation there. Dotted, we know what a dot is. Vx, and I'm going to suppress the argument just because I'm running out of room. So what is this? The divergence then, grad dot V, is actually a beautifully symmetric object. I hat dot I hat is 1. So the only thing that, and I'll write it nice and big old partials. I hat dot J hat is 0. I hat dot K hat is 0. J hat dot I hat is 0. The second term we're going to get is Vy, partial Y, because J hat dot J hat is 1, plus, same argument, IJK, only K dot K survives, partial VZ, partial Z. That's the divergence. In other coordinate systems, in the cylindrical coordinate system, this will be different. In the spherical coordinate system, in the parabolic, whatever, you know, hydraulic plumber's coordinate system, this will be different. The idea, though, is the same. You're taking a vector operator and dotting it into a vector to give you back an overall scalar. Recall that what we did before is took a vector operator on a scalar and got a vector. Now we got a vector operator on a vector producing a scalar. So this is a scalar, which means it's invariant under coordinate transformations. So no matter what coordinate system you use, that's really at the end of the day the same operator. Excellent work by nature. All right, so what does this thing mean? This is where the rubber meets the road, and this is a very this is a somewhat time-consuming exercise, but I think it's well worth the ideas that have to be presented and that you have to wrap your mind around to make progress. Who am I missing today? Is everybody here? Am I missing people? Who's not here? No, everybody's here. No, Jose, there you are, Jose.
Yeah,
Actually, I
I'm
invite
here.
everyone to be here. So let's see what this means. I want to now take, you can imagine this any way you want, but I'm going to have a vector field. You can think of fluid flow. You can think of pick your vector, wind, whatever you want. And in this vector field, so everywhere in space, I have V, X, Y, Z. So I have a vector field. And right over here, I'm going to draw a little box. In fact, I can draw a bunch of boxes, but I'm only going to look at this one. I can make boxes everywhere. I can split this volume up into a bunch of little boxes. But I'm only going to look at one little box, and I'm going to draw it bigger. And I'm going to draw it bigger, but you should not think this is macroscopic. This is a infinitesimally sized box. I'm actually going to put this in here. This is fun. Did you guys have those etch-a-sketches when you were a kid? I always see these things on the YouTube of these guys doing these etch-a-sketches, and they do like the Mona Lisa, and I barely can draw two axes. And through this box, I'm going to pick one vector that goes through the middle of it. So I've got one vector field that goes through here. Maybe it comes in the left-hand side, and maybe it goes out the right-hand side. Could go out the top, could go out the bottom. I don't know. So I'm just drawing the one though. What I do know is there's an infinite bunch of vectors next to it because this is a vector field, not just a single vector. But I'm going to look at the one that goes through the point in the middle. This is going to be a dx on this side. Let's see how I drew it. Did I draw this picture in class? No, because I didn't know how to draw yet. Maybe I'll throw some pictures in there. Okay, so this will be dx. This will be dy. And the depth part of it will be dz. So there's my box. Okay. Yeah, that's good. All right, so let's try this. I'm going to make sure. Okay, so I'm only going to look at the left and right faces anyway. And I'm going to ask in this box, what is the net flux through this box? Let me go back. If you don't remember from general physics 2, the flux through the box, the flux is, this is finite, is from a vector field, is v dot n hat dA. So if I have an arbitrary surface, this is a surface, it's not a curve. I don't know how to, there, that's better. And I have a vector field, maybe inside of it, maybe through it, it doesn't really matter. What I do to get the net flux is evaluate the vector field. I don't even want to use XYZ. So I evaluate the vector field on the surface of that particular object. Maybe it's three-dimensional. On surface. I dot it onto a normal vector everywhere on the surface. And then I integrate over every contribution on the surface. Add them all up. Piece by piece. Numerically, if you were to try to do it that way, you'd have to sit there and take a little area, calculate the normal vector. By the way, you know how to calculate the normal vector. Ah, Tim Curry died. I just saw it go across my thing. If you don't know who Tim Curry is, he was Dr. Frankenfurter on Rocky Horror Picture Show, and he has a tremendous number of credits. So they always hear this thing of you die in three. So Dolly Parton went yesterday, Tim Curry went today. A legend has died. Two legends in 48 hours. I hope Norm Macdonald's okay. Norm died several years ago. I guess that so he'll be fine. So let's calculate this. How do we calculate it? It's a bigger issue. So what I'm going to do is look at the flux through the left box and look at the flux through the right box. I'm sorry, the right side and the left side. So the net flux through here, let's go back and look. I need to evaluate the vector field, whatever the vector field is here on the right side. So on the right side, on the right face, if you will, V will be V. Remember, this point in the middle is XYZ. So I'm going to go a half step over. On the left face, I'm also going to need it. And I'll put V right here and V left. Just because I think I did that. I didn't actually do that in the notes, but this might help. V left, I need to evaluate it back here on the left face, which means I have to take a half step back. This is actually over 2. X minus dx over 2, and then y of z. Now you should stop, and I'm going to give you 10 seconds to tell me what the normal on the right is and the normal on the left. 5, 5. Okay, so the normal on this face right here is in the I hat direction. I'll draw it right on it actually. So the normal on this face is I hat. The normal over here is minus I hat. Last question. What's the area of this little face? Watch me for a second. I'm looking at this face. Okay. I'm looking at this face. This is delta y and this is delta z. Okay. I'm looking at this face right here. That's the x direction. That's I hat. On the other side, it's minus I hat. In order to complete this dA, I have to do this. This direction is delta z. This direction is delta y. So the dA in that face, in both cases, dA is just dA. It's dy dz. So if I sit here and write out, I think I use deltas in the notes. I don't think it makes any difference. So the net flux through those faces. By the way, I want you to notice when I write this down, it's not this one minus this one to get the change. It's the total. When you calculate a flux, you add everything up. The minus I hat does the lifting for you. That's what takes care of the signs that it starts to look like a net flux, but you have to add them. So the net flux, I'll call this delta flux through the X face, is this. V X plus dx y z dot I hat plus V X minus dx over 2 y z dot minus I hat. And then I need the area. So I've checked off this, I've checked off this, I've checked off now dy dz. I'm done. You say, okay, that's great. Now what? Now we start simplifying this. First things first. When I dot an I hat with any vector, and I'm going to do a little trivial example right here. Vx I hat plus V. I know you understand this. I don't care. I'm doing it anyway. K hat. Whenever you dot an arbitrary vector with an I hat, what does it do? And I like to introduce this word now. It projects out a particular component. I hat dot K hat is 0. J hat dot I hat dot K hat is 0. I hat dot J hat is 0. I hat dot I hat is 1. So this is just Vx. And this is harder work for me than it is for you. But the sacrifices I make, Y and Z, and now I'll put a little label here, is Vx. Then I have minus. Where's the minus coming from? The minus is coming from that minus I hat. A little vector over that. Minus Vy, oh, Vx, x minus dx over 2, Y and Z. and this multiplies dy dz. Now for the dreaded Taylor expansion. I'm going to do it down here and erase it later. F plus dx is equal to f evaluated at x plus dx df dx. That's all there is to what I'm about to do. It's window dressed up. It's got all kinds of stuff on there. I almost cost myself $1. It's got all kinds of stuff on there. But at the end of the day, it's still just a function. It is subject, however, to one modification as compared to this. We are in three, not one, not two, but three variables, which means if I change one and leave the other alone, I no longer am using a df/dx. What should I be using? Mr. Euler knows this. Contribute to the class, Mr. Euler. Instead of a regular derivative, what kind of derivative should I be using? Starts with a
Mm,
P. I don't
Yes,
have that kind of patience. It's a
it's a
partial. By the
partial,
time
yeah.
you get to the thing and do it, I already want to know the answer. Okay.
Okay.
It's a partial. He knew it. Believe me, he knew it. So this is now delta flux through the right face, through the x faces, is V of x evaluated at the original point plus dx partial Vx partial x. And we stop at first order. And I'm going to suppress actually, I'm going to suppress the arguments. We all know these are functions of x, y, z. Let's just make this a little bit easier to do. I did not suppress all the arguments in the notes. I'm on equation 13 minus Vx minus, because the Taylor expansion has a minus in front of the dx over 2. Close that up. Dy dz. This is a miracle. It's a privilege. It's a privilege to see these things. It's a privilege to learn this stuff. It really is. Vx minus Vx is 0. Minus a minus is plus. So the flux through the faces along the in the x sides, the x sides are then 1 half plus 1 half. So that is dx partial Vx partial x times dy times dz. And I'm going to call dx dy dz. What's the physical interpretation of dx dy dz? It's the volume of that little block. It's the volume of the little block. So this is partial Vx, and I'm just going to use shorthand notation here. I'm going to call dy dz dx the volume d tau. If we do it for if we now look at the top face, if we have a bunch of vector fields, come on, over here. No matter what it is, maybe it's got a component like this, maybe it's got a bunch of, think of water, but for the vector passing through that point, by symmetry, you can repeat this argument for the y and for the z. So by symmetry, if you do all 6 faces, the y, no, I guess the y, no, the y top and bottom and the z top and bottom, you will get partial Vx partial x plus partial Vy partial y plus, what did we just call this? Partial Vz has a name. We just defined it. D tau. And this is grad dot V, D tau. So here's what you do. This is what you do. You go to the middle of for those of you who work in fluid dynamics, I have an engineering student, and it's an interesting conversation I have with him. He sees things differently than the physicist. He's smart. Um, Go to your aquarium and look at and turn on the little, I don't know anything about food. Let me go another direction. Go to your yeah, no, go to the, what's another thing? A pool. Go to a pool. An aquarium and a pool are the same thing. Why am I making this difficult? What should I use for a fluid for inside of a box? What should I use? Somebody help me out here. The aquarium, okay? Who's on an aquarium? Okay, an aquarium. The
That's
fish
an
are swimming.
accord. Well,
Think Nemo. You're in there. You got the any of y'all everybody seen Nemo? The fish, the movie about the fish.
Yes,
Yes.
Reagan, have you seen Nemo?
I have.
Jose, have you seen Nemo? I can't hear anybody. Maybe my volume's down.
Yes, sir.
Is everybody okay? So think of an aquarium. I just spent a minute of valuable class time not coming up with a good examples. Think of an aquarium and think of the little motor making the water go and think of the fish swimming around. So everywhere the water's flowing. So there's a vector associated with the velocity of the water at any point. I want you to go and zoom in at a little point inside of that aquarium with all the fish and the water moving around. So you're going to go in there and you're going to draw a little box at any point. What point? I don't know, pick one, XYZ, 1.2, 3.7, and -2. So you go in there and you put a little box. And if you want to know how much water is flowing in and out of that box, you calculate grad dot V, and then you multiply it by d tau to get the total. So it's kind of the flux per unit volume, but the little volume thing is really just an attendant artifact of the fact that you're doing it in 3 dimensions. So let's talk about that interpretation. If you have grad dot V is equal to 0, what does that tell you? That tells you water coming in is the same amount as the water coming out. And in fact, that's such an important idea for water that it is called the incompressibility condition. So the amount you push in is the same as the amount that comes out for water. So the net flux through a box of water in is amount out. Suppose you have grad dot V is equal to 0, not equal to 0. Suppose grad dot V, if grad dot V is equal to 0, in equal out. Doesn't have to be a box. Suppose grad dot V is greater than 0. Greater than 0. So out then is bigger than in. You know what you have? You go in that aquarium, you put somewhere in there, there's a fish with a water gun. You draw that little box, and you know for water, grad dot V is equal to 0. So in here, there's a fish with a water gun, and he's spraying water out inside the box. So in that box, there's more water coming out because you can't see the fish. He's invisible. So I have an invisible fish with a squirt pistol shooting water out. Now suppose grad dot V is equal to 0. Less than 0, sorry. What I have then is I look at that box and I see the water and I see out is less than in. So what's happening now? I'm losing water. So my fish in here, you know what he's doing? He's got a bucket and he's collecting it. So he's sitting here with his bucket and he's grabbing the water and he's putting a lid on it and he doesn't let it come out. So that's the interpretation of divergence. It's the vector field flux per unit volume through some little tiny amount in there. So that is going to be important when we talk about electric and magnetic fields. Why would that be? I want you to think for a second about a point charge. Here's Q. We have seen many, many times in our lives that if we draw this circle, we get positive flux. If we have minus Q, we get negative flux. Electric fields start on positive charges and end on negatives, just to get to electrostatics as as an example here. However, if you have plus Q and minus Q together here, and no matter how you draw, the amount out will be equal to the same amount in because the net charge is equal to 0. That's Gauss's law. That's Gauss's law in a nutshell. All the rest of it is a complicated detail. That's all there is to it. That's why, by the way, that the net flux of a magnetic field is 0 because a positive and a negative charge are always always appear in pairs. Okay, so that is very nice. What's even nicer is this. Okay. Here is my volume. I'm not going to do this rigorously. And I'm going to take that volume and turn it into a whole bunch of little boxes in here. And I'm not really that good, but these are all boxes. Okay, look. No, I don't want to do it that way either. So now I'm going to have a vector field coming through here. All right. All right, let's go. So now I'm only going to do this for three boxes. Will it make a square? No. Gotta make a square. It did. Be patient with me. One more. You see how they're deteriorating? Entropy is winning. Okay, so we three identical boxes. I look right in here and I got these three boxes. So this is a magnified view of this. And I got a vector field flowing through these boxes. And I'm going to calculate the net flux through all these boxes. So here, son of a gun. So the net flux here is box one plus box two plus box three. Box one, box two. Am I doing on time? Doing good on time. So I evaluate this on the left face, and then I evaluate the vector field on the right face. So I have here for phi 1 left plus phi 2, phi right 1, box 1. Then I look at this face. You know what's true about that face? It's common to 1 and 2. So in this case, I'll have phi 2 left, oops, plus phi 2 right, which is evaluated here. Then I have, see that face? That's common. The right face of 2 is the left face of 3. Phi 3 left plus phi 3 right. And now here comes the crux of the issue. Because the unit vectors on this first box point that way, and for second box that way, over here they point that way and that way. These two are the same and opposite. These cancel. These two are the same and opposite. They cancel. So all I'm left with is the left face and the right face. And you can do this all through this entire box. I'm only going to draw. That looks like a mutant ninja turtle with his. That looks like Donatello. Look at him. He looks like Donatello. Now he doesn't because that's the wrong notes for a turtle. So all these internal fluxes cancel, and the only place I get anything is at the surface. So if I were to be patient and go through that entire box, the entire box, and sum over v dot n hat dA through every single face, the only place I would get anything is at the surface. So I would only get v dot n hat dA evaluated on the surface. But what did we just say v dot n hat dA was? V dot n hat dA is the same as adding up. On A1, that's the same as adding up all the volumes of grad dot V d tau. And though we haven't done it rigorously, what we've done now is said if I add up all of these, face, face, volume, face, volume, face, volume, face, volume, face, volume, toy boat, all the volumes, all the faces, eventually what I will get is in the infinitesimal limit, v dot n hat dA is equal to, that's a pronounced equal sign. I'm so enthusiastic about this identity, grad dot V d tau. This is what's called Gauss's theorem. You will find it, let me tell you where it is. You will find it on the top of, I believe, bottom of page 15. Equation 16, bottom of page 3. Let me tell you why I'm checking this out for my own edification. I used in the notes, I could have been consistent, but I wasn't looking at the notes. Equation 16 has a sigma here. In a lot of books, you will see sigma for area and tau for volume. And in general, here was the issue, just so you know that, I'm senility is approaching. There's two ways I could have done this. I could have called it dA for the area and dV for the volume. But then in the middle of it, I realized I used a vector v, and I didn't want v and dv to be the same thing. One was a volume, the other was a vector field. So then I said, too late to fix that. So I stuck with d tau, but then I couldn't use sigma here. If you're using Greek on one side, I would like to use Greek for the other side, but I didn't. So it's an inconsistent notation. In equation 16, however, I fixed that up. So you'll see in equation 16, it's sum over all faces is that thing, and that is Gauss's theorem, and we will use that repeatedly. All right, so that's v dot n hat. This turns out it's not apparent looking at it. This is actually Gauss's law. It doesn't look like it, but this connects what's called the differential form to the integral form of Gauss's law and Maxwell, and it's one of Maxwell's equations. So we're getting there. So that was a long and difficult exercise to some extent. Maybe it wasn't difficult for you. I will only tell you this. I spent several weeks one summer with a book, Lorraine and Corson. That was my E&M book, learning how to do this blind because I was obsessed with it. You don't have to be, but I think it teaches you so many outstanding techniques that relate to just about every branch of physics. This understanding of Taylor expansion, this understanding of keeping the lowest order. Sometimes there are occasions, I think, where you have higher order in the differentials, dx squared, dx, nothing ever higher than dx squared. And this whole notion of evaluating fluxes and looking left, looking right, and looking, I think that's an invaluable exercise. It's an extremely good thing to be able to do on your own. It teaches you a good deal. In fact, we're going to proceed through the next, example one, vector field within a cube. Let's look at example one. Okay. So I have this, I will post it up to, give me a second. Example one, chapter one, example one. I did a bunch of chapter one, example one. So I will have this up for you. Actually, we can do it now. I'll put it up for you later. So here's example one. Normally I like to do it in real time, but I forgot that I had it. So let's look at example one. Here's a vector field. The vector field is V is equal to xy squared I hat plus zj hat. And I want to look at this vector field on a cube of side L equal 2. Okay? So this is 2. How are we doing on time? We're doing good on time. 2 and 2. All right? So I didn't pick some easy one. I picked, this is not hard, but I didn't pick one that had a special thing that allowed me to work it out quick. I actually picked an arbitrary one. I don't have a y component. That's where I cheat a little bit because I want to be doing, 3 components when 2 would do. So let's calculate this. We're going to calculate the flux through the x and the flux through the y. So the flux through the x I call phi x, and I'm going to calculate this on the two faces that are relevant to calculating the flux. So I'm calculating the flux through the right face. The flux through the right face is the vector field evaluated on this face. That face is the right face. It's over here. That's the I hat. What is the area? The area, as I said before, is dy dz. There's nothing new under the sun. When you get confused, just write it out. I don't know if I told you that, did I say that I would have I would put a ream of paper out for the class? Was it that my stat mech class or this class? And I said I'd have a whole ream of paper for you if you wanted it. If you don't know what to do, write something down. If the only thing that's preventing you from writing it down is paper, I'll give you the paper. Start somewhere. You know what's a good place to start? The definition. Can't be any more primitive than that. So there's the flux. So I have it. It's not a sphere, so it's not as simple. We have to do a right face and a left face. So the right face is v dot I hat, and the area is dy dz. The left face is, and I'll put this up on canvas, is v dot minus I hat, dy dz. All right, let's look at that. So the x component of the vector field is right here. And I'm going to be cleaning this stuff up as I go, actually. So that is xy squared, dy dz, and I need to evaluate this at x is equal to 1. Why is x is equal to 1? Because that's this face. The x face is right here. That's why I picked it, by the way, to have a cube of side 2, so I could say x is equal to 1 and x is equal to minus 1. I didn't want to use a half and a half. I'm not good at math, so, fractions throw me. Next piece. That minus I hat here turns into a minus on the outside there. Just cleaned it up. Same vector field. Isn't this 0? No, it's not. You know why it's not 0? It's two different faces. That face is at x is equal to minus 1. There it is. So currently what I have is an integral I have to evaluate over dy dz. You can't really do that integral unless x is nice and simple. And this is where I did cheat a little bit. I made it x is equal to 1 for the side of a square. And I put directly x is equal to 1 there. I evaluate it at x equal to 1. And then I do the integral. And I believe that's it. Yeah, that's only left a function of y squared. So where does this 2 come from? That 2 comes from integrating dz. That 2 comes from integrating dz. Z goes from 1 to minus 1 to 1. Or minus, so it's 1 minus a minus 1 to a lower limit to upper limit. So that's 1 minus a minus 1, that's 2. However, y is not so simple. I have to evaluate it. So when I evaluate that, I get y cubed over 3 from plus 1 to minus 1, and I do the same thing on the other side. So now I have the minus from the flux, and I get a minus 1 because x is equal to minus 1. Y again is 1 to minus 1, integral, minus 1 to 1. And then I have the same thing. I won't evaluate that trivially. It's 8/3. So you get 8/3. You just put in plus and minus 1, that's 2/3 times 2, that's 4/3, that's 8/3. Okay, good. The y one, the y component is here. That's 0 because what I have when I do that is z surviving. So that is z, and there's minus z. And in that case, you don't have anything to worry about. That actually is 0. That actually is 0. And then when we do this, because notice, by the way, notice that's, how do I want to say this? Z is odd. So when you integrate it, it's an odd function over symmetric limits. I may come back and do that. How are we doing on time? All right, got a minute left. I'm going to revisit that next time as a clarification. So now, if we did this right, grad dot v d tau is equal to 0. It only takes a second to calculate grad dot v. Remember, grad dot v is partial x onto vx. Vx is x y squared. And then partial y of z. That's equal to 0. And then I need dx dy. Notice that's a volume this time. So the derivative of x with respect to x is 1. So I integrate y squared. So this is minus 1 to 1, minus 1 to 1, and then minus 1 to 1. The dx dy gives me 2 times 2 because it's 2 on a side. And then y cubed over 3, when I integrate that, is going to give me 1/3 plus 1/3, which is 2/3. 2 times 2 times 2/3 over 3 is 8/3. So it all works out. I'm actually going to go a minute long. Why is this equal to 0? This is equal to 0 because when you do the dx, and when you do the dx, that is just going to give you 2. When you do the z squared integral, that is z squared over 2. Got a minus here, minus 2 times z squared over 2. Both of the limits are the same, minus 1 to 1, and that will give me 0. Odd function over symmetric limits is equal to 0. That's a good thing to know, by the way. When you evaluate an odd function, oh, I can't. This is pristine and beautiful. I can't. This is example 1. I can't just be drawing random things on there. But when you do a odd function, over symmetric limits, that's minus, that's plus, minus a to a. That saves you some time. All right, we'll stop here. I am probably gonna, I think we're far enough where I can at least throw a couple of homework problems up on Canvas pretty soon. So keep that in mind. And I will see everyone Wednesday. And again, I want to thank you all for working with me today remotely. It's not my first choice ever. I'm cramped. My normal dogs are usually back here passing gas. It's just not the most hospitable environment, and I can't go to another room because my thank you, Jose, because my daughter's here with her sister from the University of Oregon, and they're loud watching playing Fortnite, whatever the hell that is. Is Fortnite? Anybody play Fortnite? Do you know what it is? Really? All right. And scene.